Okay, so we're going to do another problem. Here we have a two-dimensional problem. So we have an XY plane, and we have three charges, Q1, Q2, and Q3. So Q1 and Q3 are negative, Q2 is positive. Their values are shown here. And I want the force on 3. So what is the force on charge 3? Now, just to avoid cluttering the board too much, I put the units here, like this is X in meters, this is Y in meters. So like this charge Q2 is at, 2 meters along the X-axis, and charge 3 is 1 meter along the Y-axis. So I didn't write the numbers down, but just from like the tick marks. Okay. So basically, I can draw a dashed line showing we have a triangle here. And we want the force on charge 3. So, I'm going to use a different color. I'm going to call this F31. And this is F32. Okay, so F31. So again, these are both forces on charge 3. So if you look at the interaction between 3 and 1, they're both negative charges, so charge 3 is being repelled from charge 1, so the force is upwards. There's a line, it's along the y-axis because these charges are both on the y-axis. And similarly, here we have a negative charge and a positive charge. So it's going to be on this line connecting them, and charge 3 is attracted to charge 2, so it's going to be in that direction. So basically, all we have to do is find F31, F32, and add that. The problem is that F31 and F32 are vectors in a two-dimensional plane. So what I'm going to do to start out with is make a table. I'm going to say F31, F32, and let's just say F net. And here we have X and Y. So right off the bat, let's look at F31. We know the X component is 0, and the Y component is positive. So we can tell just the direction of F31, it's pointing in the positive Y direction. It has no X component, so that's 0. That one is positive. If we look at F32, it's going in this direction. So we go in the positive X direction and the negative Y direction. Now, we don't know the magnitudes yet, but I'm going to just put these, I like to do it this way, you don't have to. But just so you don't forget later, at the very least, just write it down so you know what direction each component is going to be. So yeah, we can break F32 into components. We have one in this direction and one downward. Okay, and once we fill out this table, the net force, we just add these to get the X component of the net force, and add these two to get the the Y component of the net force. So our goal is to basically get that. Okay, so now we want to find the magnitudes of, say, F31. Let's do that. I'm going to have to write a little smaller here. So F31, we have our usual constant. And then we have, Q1 times Q3. So again, we have 3 microcoulombs. We don't put the minus sign. And then here we have 4 microcoulombs. So again, I'll write it as You know, just like 3 coulombs over 10 to the 6 and 4 coulombs over 10 to the 6. And now we're dividing by the distance squared, which is just a meter squared, so I'm going to just put it here. Because this distance is 1 meter. And also, just because I think the units will work out a little nicer this way, let's say 1,000 millinewtons in 1 newton. Coulomb squared, we got rid of that. Those cancel each other out, and we're left with millinewtons. Also, 10 to the third, or 10 to the 9 times 10 to the third is 10 to the 12th. On bottom, 10 to the 6 and 10 to the 6. So that's why we converted to millinewtons. Just makes all the numbers work out nicely. So here we have 9 times 3 times 4. 12 times 9, that's 108 millinewtons. So I'm going to write it, I'm going to wind up erasing this. I'll have to, I think. But if we just multiply the numbers, we have 108 millinewtons. Okay. Now, and we're kind of done with this one because we already know it's entirely pointing in the y direction. So we can just write 108 here. Now, I don't have room to write the units. Everything's going to be in millinewtons. So I should write them on each of these, but just no room. So yeah. You never want to ignore units, but I guess not writing them down in certain circumstances is okay. All right, now that was the easy one. Let's look at F3-2. This is going to be a little more complicated for 2 reasons. Well, let's start. So we have our usual constant, 9 times 10 to the 9th. And then we have Q2 is 4 microcoulombs, or 4 coulombs over 10 to the 6. And then -6, but we ignore the negative, 6 coulombs over 10 to the 6. But now we have to divide by the distance squared. So what distance are we talking about? We're talking about the distance between charge 2 and charge 3. And so we have to find that by using geometry. We have a right triangle here. So I'm going to draw this triangle. Basically, we have Q1, or that's the origin. Here's Q2. Here's Q3. We have a nice right triangle. Now, it might not always work out quite so nicely, but I arranged it so that these formed a right triangle. Just to make it a little easier. Okay, so this is a right angle. And we know this is 1 meter, and this is 2 meters. Just from looking at the picture, like 1, 2, and just 1. And so this I'm going to call R23. That's the distance between charges 2 and 3. Now, we don't even need to know what this number is. Just from the Pythagoras theorem, we can say R23 squared is equal to 2 meters, in parentheses squared, plus 1 meter in parentheses squared. If we work that out, 2 squared is 4, plus 1 is 5. So this distance squared is 5 meters squared. Now if we wanted this actual distance, we take the square root of that. But the formula we have in R squared, so there's no reason to take the square root and then square it again, and we'll just be back to 5. So this number here is 5 meters squared. And then let's cram that conversion factor in there. 1,000 millinewtons for 1 newton. So again, I'm going to quickly just cancel out the units. Also 10 to the 9 and 10 to the 3rd, that cancels that out. We're left with millinewtons. So let's see, we have 9 times 4 times 6 divided by 5. That'd be in millinewtons. Let's see what this, if we can simplify this. Here's what I can do. 4 over 5 is 0.8 times 9, that would be 7.2, and then times 6. Yes, we're getting around 43.2 millinewtons. So I'm going to write that down somewhere. Let me just double check. Yeah, 43.2, I believe that number. So I'm going to write that down here. F32 is 43.2 millinewtons. And I'm going to erase this junk here. We don't need this anymore. This is the square root of 5 meters. Kind of want that. Okay. And I'm going to write our force on this triangle as well. So this is our force. We know the magnitude of this force. It's 43.2 millinewtons. But, you know, to add forces that point in different directions, you know, by far the easiest way to do that is to break them into components. So what we need to do is we're going to have an x component and a y component. We're going to say this force, I'm going to get rid of that. I did write it there for a reason. But, yeah, so this is F32. So we'll break it up into an x component and a y component. So different ways to do this. One, we need an angle here to define this direction. Let's define this angle to be theta. You can do either one. I mean, it doesn't make a difference. If you know one angle, you know the other. It's a right triangle, so the other two have to add up to 90. So let's define this angle to be theta. Now, how do we find theta? There's different ways we can do this. If we actually want to find theta, we'd want to take an inverse trig function. And there's different options. We could say, one way we could do this is say sine of theta is going to be 1 over the square root of 5. So remember, the hypotenuse is the square root of 5. So sine is opposite over hypotenuse. We could say cosine of theta is 2 over the square root of 5, or tangent of theta is 1 over 2. So tangent, opposite over adjacent. Now, if we want to find the angle, any of these will work. However, I'm going to say this is the best way to go, taking the inverse tangent. Now, why is this the best option out of the three? Well, we can go back to the original problem, and we have this triangle here, and we know this side is 1, and we know that side of the triangle is 2. Now, we also know that the hypotenuse is the square root of 5, but we weren't given that in the problem. We had to calculate the hypotenuse, and what if we screwed that up? Well, we didn't. It's a simple problem, but it's the thing, if we screwed up this number, then we'd screw up the angle as well. So it's just an additional mistake. So this number, we're just using numbers that were given to us. We're a little bit safer going this way. So tangent of theta is 1/2, and we can take the inverse tangent and get the angle. But what I'm going to do, I'm going to write this down. Here's another way we can do this without really finding the angle. Let's look at F32x. I guess I'll write it like this. So here's our force. We want the x component of that. That would be F32 times cosine of the angle. So like this angle is the same as that angle. Again, these lines are parallel. This, this is just the x-axis. And, we broke it up into a component parallel to the x-axis. So that's definitely parallel to that. And so, alternate interior angles or something, they call it in geometry. I just know these two angles are equal to each other. And so, this angle, or this component of our vector is adjacent to the angle, so we use cosine. So we could say that this is equal to the magnitude, which is 43.2 millinewtons, times cosine of theta. What's the square root of 5? I'm going to check something. I think it's 2.3, but I'm going to start here. Yeah, 2.2 squared is 5.84. That's close. We'll go to 2.3 squared. That might be too high. I don't want to see which is closer. It's kind of in the middle. So square root of 5, let's just say 2.2. A little bit off. Okay. So we're going to end up with around 20 millinewtons. I don't have a calculator, but you can always check and get a more accurate number here. But the x component, I'm going to say 20 millinewtons. Let's just check. If we go with 20 times 2.2, yeah, that'd be around 44. We're pretty good there. So the x component was around 20 millinewtons. A little bit of a round off error. But, close enough. Now, let's look at the y component. Well, that would be F32 times sine of theta. Right. Sorry, I did make a mistake. Cosine of theta, that would be 2 over root 5. So this would be 40. Sorry about that. Okay, and now here we have F32 sine of theta. So this would be 40, here, this should be over 1.1. So here we have 43.2 millinewtons. And now we just have divided by square root of 5, which is around 2.2. This one's going to be around 20 millinewtons. So again, with a calculator, you can easily check. These numbers, I think, are fairly accurate. Yeah, I don't know, a calculator, so. But yeah, check those. It should be fairly close. Okay, and now the last step is to find the net force. And once we have it in component form, it's easy. We just add the columns. So here we have 40 millinewtons. Here, 108 minus 20, that's 88 millinewtons. And so the net force, we have an x component and a y component, both positive. So the net force is going to be something like this. Now, one thing we could do with this net force is we could convert this to polar form, where we could find the magnitude of that force. So I'm going to erase all this stuff. So to find F net, we have the components are 40 and 88. So we'd have 40 squared plus 88 squared. Again, everything's in millinewtons here. So you'd add these up and take the square root. That would give you the net force. And again, our net force, we have an x component of 40 and a y component of 88. So to find the angle, I'm going to call that phi. We used theta earlier. So we could say tangent of phi is 88 over 40, and then take the inverse tangent of that to get the angle. So that would be, to convert it to polar form. Now, just one more thing I'm going to say about this problem. When it comes to converting to polar form, you definitely want to draw a picture, because it involves taking an inverse tangent. And just real quickly, I want to talk about inverse tangents. We're done with this problem, but this is something that could come up in a different problem, just depending on the details. So let's say we plot tangent of theta. So we have 90 degrees, or pi over 2. Now remember, cosine of 90, or cosine of pi over 2 is 0. So that's going to be an asymptote. Same with minus 90. So if we plot tangent function, not the best picture, but it's basically going to look like this, where there's all these branches. And here, to convert our, so again, this is basically tangent. Here, let's say we have x, and this is tangent x on the y scale. Okay, so this is basically what it looks like. And again, we frequently take inverse tangents. And now the question is, does this function here have an inverse tangent? And the answer is definitely no, it does not. Now, it might seem strange because your calculator has an inverse tangent, you learn all about them. And hopefully if you've taken trig, you understand why this does not have an inverse. Or even, if you just take an algebra. Because the idea of an inverse function. So first let's talk about functions. Is this a function? The answer is yes. The easiest way to see that is something called the vertical line test, where you can draw any vertical line through this graph, and you're only going to cross the graph at one point. So it doesn't mean you can draw a vertical line. Like, let me give you an example of another graph. What if we have something like this? Now I can draw a vertical line and only cross once here, but that doesn't mean this is a function, because there's a line here that crosses at multiple points. So this is not a function. And the reason why it's not a function, the reason why the vertical line test works, is the whole idea of a function is you have an input and an output. Like, say we have f of x. It's like we plug in x. Let's say y is f of x. So we plug in x and we get y. And there can't be any question about what y is for some whatever x we plug in. And so in this case, like say that we plug in this x value, the y could be here or here or here. There's three choices. We don't know what y is for this x value, so it's not a function. Okay, but tangent's fine. Every single vertical line that we draw is going to hit at most one point. Or 0. We draw a vertical line and an asymptote. Otherwise, we're going through exactly one point, never more. So this is a function. And again, like I mentioned, if we have y equals f of x, then you can think like we have an x, and that's going to map to y. So say this is x. And the function does this. It takes us from x to y. So like say x is 2. F of 2 is whatever. So we plug in 2, we get y. We plug in x, we get y. Now what the inverse does is it takes us back. And so in order for an inverse to be a function, it has to pass what's called the horizontal line test. And so again, we draw a horizontal line and we can only cross our graph at one point. And this totally fails. You can draw a vertical line here, and we actually cross an infinite number of times. Here, here, here. And again, this is a periodic function. It just keeps repeating itself. So, yeah, we can't have it cross more than one time. We crossed an infinite number of times. That's a problem. And so the tangent function, as we've drawn it here, simply does not have an inverse. So, why do we say there is a thing called an inverse tangent function? And the answer, because it's extremely useful and we need it. So what we do is we get on our eraser and get rid of this, and we get rid of that. Basically what we're doing is we're restricting our domain to be, I'll just write it here, between minus pi over 2 and pi over 2. And if this is our function, it only exists in between those two values, now we pass the horizontal line test and we can define an inverse. So, yeah, there's no inverse for something like, let's say we have y equals x squared. You know, that would look like this. It's like, say we have a nice parabola. It's like if I tell you x equals 2, you know y equals 4. But if I tell you y equals 4, do you know what x is? No, maybe it's 2, maybe it's negative 2. We don't know. So, yeah, this does not have an inverse. Fails the horizontal line test. Now, why do we need to know this? You know, why do we care? And the answer is, when we take the inverse tangent, we're going to get an answer between minus pi over 2 and pi over 2. That'll give us an answer, but that might not be the one we want. So let me give you an example of an actual problem we could come across in physics, similar to what we were doing before. Let's say we do that whole process. Remember, we got a net force that was pointing in the x and y direction. Let's say we do that whole process and we get our net force. Here's our net force. I'm going to write it this way. Let's say, in whatever units we have, let's say we have minus 4 in the x direction and 5 in the y direction. And remember, tangent of theta, that would be the y component over the x component. So if we just kind of blindly plug this in, the y component over the x component, we'd have 5 over minus 4, and we would take the inverse tangent, and our answer would be wrong. Now, why would that be? Let's graph this. So like, here's our xy plane. And the net force, we go minus 4 in the x direction and up 5 in the y direction. So we're going to end up over here. The net force points in this direction. Now, if we take the inverse tangent of 5 over 4, I don't know what the number is, but it's going to be around, like, say, 55 degrees, minus 55 degrees. So remember, we measure angles counterclockwise. Let's say theta's around minus 55 degrees. Like, the inverse tangent of 1 is 45. Tangent of 45 is 1. Here, let's forget about the negative. This is bigger than 1, so we have an angle bigger than 45 degrees. Let's just say it's around minus 55. And again, we measure angles going counterclockwise here. So a negative angle means we go clockwise. And this would be our angle here. So basically, if we just blindly plug in this formula, tangent of theta is the y component over the x component, we'd get this angle here, we'd be saying our force is pointing in that direction, when it's actually the exact opposite. And that's because we have this issue where, like in the real world, where we have a two-dimensional problem, the force can point in any of these quadrants, but the inverse tangent is going to give us an answer in either quadrant 1 or quadrant 4, just because of the way it's defined. It's like both of these angles, both of these forces, here we have minus 4 comma 5. This one would be 5 comma negative 4. So like if you take the y over the x, sorry, let me get this right. Yeah, we went 4 and 5. So in this one, let's say this is F1. Minus 4 comma 5. F2 is 4 comma minus 5. Now this one would point in this minus 55 degree angle. And so again, if you look at the ratio of the y component over the x component, here we have 5 over negative 4. In this case, Fy over Fx is minus 5 over 4. They're both minus 1.2. It's like that ratio is the same for both of these forces that point in exactly opposite directions. And so they're going to have the same, before you take the inverse, you have that same number. Your calculator doesn't know which of these two that you want. So if you want to find the direction of a vector, you always want to draw it. Now, another approach, which I have no idea why anyone would do this, but you could try to distinguish it like 5 divided by negative 4, or minus 5 over 4. I've actually seen it taught that way, where you try to remember, like, just memorizing a bunch of stuff to know, like, which of these two. Just draw a picture. Much easier, and you shouldn't make any mistakes doing it that way. So again, if this angle is 55 degrees in magnitude, that would make that angle 55 degrees. One way you can always express a vector is just in the standard form. So let's say our angle would be 125 degrees, because these have to add up to 180. So like in standard form, you start at the positive x and go counterclockwise. So if you want to express this in the direction in standard form, you could say around 125 degrees. Now on a test, if you just said 55 degrees and accompanied that with a picture, I'm totally fine with that. Because if you draw this picture, you know what direction the thing is pointing, and that magnitude, then I know, not just what quadrant it's in, but the exact direction it's pointing. So that's totally fine as well. Yeah. So again, a lot of steps in problems like this. And so generally just go through them kind of carefully. Make sure you know like this, the order of the steps, and then you just do them. Just be careful, because there's a lot of steps involved, and a mistake anywhere can kind of screw everything up. And so, on that note, showing work is always a good idea, because there's a lot of steps, and if you only screw up one step, your answer is totally wrong, but if I can see what you did, then it's much easier to give partial credit. Okay, but that'll be it for this topic. I think next we're going to talk about something called the electric field, but that'll be a separate lecture.